All right, let's do some applications to differential equations. So recall that this is from section 9.1, that the Laplace transform on x prime is s times big X of s minus little x of 0. I'm going to make those, my big X's more obvious, you know? And then the Laplace transform on the second derivative would be s squared times big X minus s times x. I shouldn't have put, it's x of 0. S times x of 0. And then minus x prime of 0. Okay, so those are from section 1. And the directions today are, we're going to apply these. We're going to solve the following Laplace transforms. We'll solve the following using Laplace transforms. That makes better sense. Okay, so first one is x double prime minus 5x prime plus 4x is equal to e to the 2t, and they also give us some initial conditions that x of 0 is 1 and x prime of 0 is negative 1. Okay, so what you're going to do is take the Laplace transform of both sides of this equation. So we're going to take the Laplace transform of the whole thing. And remember that Laplace transforms are a linear transformation, so that it becomes the Laplace transform on x prime and then minus a 5 times the Laplace transform of x. Well, that was double prime. This is single prime. Plus 4 times the Laplace transform on little x, and then equals the Laplace transform of e to the 2t. Okay? Not that you have to show me that whole step, but okay, so let's start with the Laplace transform on x, the second derivative on x. Well, that's this guy. So it'll be an s squared times capital X of s. In fact, I'm not going to, let's not convolute it. I just said convolute, because we had convolutions yesterday. I got, I'm just not going to put the of s. I'm just going to do a capital X and then minus s times x of 0 minus x prime of 0. So this whole part was Laplace transform on x double prime. Okay, then I've got a minus 5 times the Laplace transform on x prime, which is s times capital X minus x of 0. And then a plus 4 times the Laplace transform on little x. Well, that's capital X. And then the Laplace transform on e to the 2t is 1 over s minus 2, since 2 is the exponent in front of the t there. Okay, so this was 5 times the Laplace transform on x single prime. And then this was 4 times the Laplace transform on x, and this was the Laplace transform on e to the 2t. Yeah, hopefully that makes sense. I don't know why it looks like it's crooked. I don't know, maybe it's my screen. Okay, now we were given some values, so let's replace those, right? So your initial value is x of 0 is 1, so this guy is equal to 1. X prime of 0 is negative 1. So this is positive 1, that's negative 1. This guy is a positive 1. Okay, good enough. So that when I go and rewrite this now, I've got s squared times capital X. I'll just do that, right? Minus s times 1, so just a minus s, minus a negative 1, so a plus 1, minus 5. I'm going to distribute the negative 5 into these guys. So a minus 5s times capital X, and then a minus 5 times a minus 1, so a plus 5. I still have the plus 4 times capital X, and that's equal to 1 over S minus 2. Okay. You want to solve for capital X as your goal. So I'm going to get anything without an X in it over to the other side, right? And I'm also going to factor out the capital X, and you would be left with an S squared minus 5S and a plus 4. And I'm going to add the S. Here's a minus S. I'm gonna add it over to the other side. So a plus S, and I have a 1 and a 5. They're both positive, so that's the 6 over here. I'm going to subtract 6 like that. Okay. So again, your goal is to solve for capital X there, right? So this is like an S over 1. If I add these two guys together, I would need a common denominator. So that'll give me equals, it would be a 1 plus S squared minus 2S minus 6S, so minus 8S plus 12. And that's all over S minus 2. Over here, this guy factors as what? S minus 4 and an S minus 1. Okay, so that I'll divide both of these guys so that you've got capital X is equal to, now my numerator or denominator, I have an S minus 2. I'm dividing by S minus 4. I'm going to divide by S minus 1. Up top here will be an S squared minus 8S plus 13. Okay, so this is a Laplace transform of something, but it's not obvious right now, right? So what you're going to do is do partial fraction decomp so that it's said placeholder over S minus 2 plus another placeholder over S minus 4 and another placeholder over S minus 1. And when you go to solve these, you're going to multiply both sides of the equation by the common denominator. So multiply both sides of this guy by S minus 2 and S minus 4 and S minus 1 so that you've got S squared minus 8S plus 13 will equal A times, when you multiply both sides by S minus 2 and S minus 4 and S minus 1, on the A, the S minus 2 will cancel. So you'll have a S minus 4 and an S minus 1 left, plus B times, the S minus 4 will cancel on this one, so S minus 2 and S minus 1. And then C times the S minus 1 will cancel with the C, so but you'll still have an S minus 2 and an S minus 4. Yeah? Okay, so now if you remember how you do this is you let S be values that will cancel out the other guys. So if I let S equal 2, it would give me a 2 squared minus 16 plus 13 is equal to A times negative 2 times 1 plus 0 plus 0. So that ends up giving you negative 12 plus. So A is equal to negative 1/2. If you let S equal 4, you'll have a 4 squared minus 32 plus 13 is equal to B times 2 times 3. So B would equal, what is that? Negative 16 plus 13 is negative 3 divided by 6. So a negative 1/2 also. Okay. And then let S equal 1. And that'll give you a 1 minus 8 plus 13 is equal to 0, 0. C times negative 1 times negative 3. So C would be negative 7 plus 13 is 6 divided by 3, so C is 2. Okay, so what that means for us is I'm going to plug all of these guys in over here. So your capital X is a negative 1/2 over S minus 2 plus a negative 1/2 over S minus 4, and then a plus 2 over S minus 1. And it's definitely the Laplace transforms, right? If big X is this, then little x is negative 1/2 times e to the, we have a 2 here, so 2t. We have a negative 1/2 again, so minus 1/2 e to the 4t plus 2 times e to the 1t. You just solved it using Laplace transforms. Yay! Okay, let's do another one. I want to solve x double prime plus 4x equals 9 sine of t. And they gave us that x of 0 is 1 and x prime of 0 is negative 1. All right, so again, you'll do the Laplace transform on both sides of the equation, right? Where when you do a Laplace transform on x double prime, it's an s squared times capital X minus s times x of 0 minus x prime of 0. That's the Laplace transform on x double prime. But plus 4 times the Laplace transform of x, which is just capital X, and then 9 times the Laplace transform of sine of 1t, so it's a 1 over s squared plus 1 squared. Yeah? Okay. Now, what we know is, I know x of 0 is 1, and I know x prime of 0 is negative 1. So now this becomes s squared times capital X minus s plus 1 plus 4 times capital X is equal to 9 over s squared plus 1. Okay, your goal is to solve for capital X. So let's, I'm going to add the s over here. I'm going to subtract the 1 over here. I'm going to factor out the capital X, and I'll have an s squared plus 4. And then I've got 9 over s squared plus 1, and I'm going to add the s and subtract the 1. Yeah. Okay, so if I go to get a common denominator over here, put it over 1, multiply top and bottom by s squared plus 1 so that I can actually add the two fractions together. S squared plus 4 does not factor. Ooh, okay, so, all right, we got this though. It'll be okay. It's just going to be crazy, but whatever. Okay, so this is I'll now have an s squared plus 1 as my common denominator. Up here I'll have a 9 plus s times s squared is s cubed plus s minus s squared, and then a minus 1. Yeah, so that big capital X is an s cubed minus s squared plus s plus 8 over, I have the s squared plus 1 down there, but then I'm also going to divide by the s squared plus 4 there. Make sure I didn't do a typo. S cubed minus s squared. Blah, 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 yep, 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 boop, boop. Okay. Partial fraction decomp. But these are both irreducible quadratics. So do you remember you can't just put a over the fraction, right? Or instead, it'll be as plus b over, I'm going to flip these guys just because I'm going to be a pain in the butt to you, because that's what my notes have. And then if I don't, then I can't confirm myself as easy. And then a cs plus d over the other factor. In the end, it won't matter, right? But anyway. Okay. So far, okay? Multiply both sides by the common denominator so that you get, start a new page. When I multiply both sides by s squared plus 1 times s squared plus 4, I'll have s cubed minus s squared plus s plus 8 is equal to as plus b times s squared plus 4 will cancel, so I'll still have an s squared plus 1 though, and then plus cs plus d times the s squared plus 4. All right, so this is the kind where you can't just plug something in, right? There's nothing you can plug into s to make that go away and become a 0. So here's when we're going to distribute it all out and then equate coefficients. So this becomes as cubed plus as plus bs squared plus b. Do the same thing over here. Distribute. It's a cs cubed plus 4cs plus ds squared plus 4d. Okay, so now what you want to do is to be able to equate coefficients, you need to group them. We've got s cubed. I have an a and a plus c. So a plus c is the coefficient on s cubed. Yeah. Then I have s squared times b plus d. I have an s times a plus 4c. And then I have my constant, no s, would be b s plus 40. Yeah, and to equate coefficients means I've got a 1 on the coefficient on s cubed, so that means a plus c must equal 1. I've got a -1 on s squared, so b plus d must equal -1. I have a 1 on s, so a plus 4c must equal 1. And then my constant is 8, so b plus 40 must equal 8. All right, so now we need to solve this system, right? I've got a plus c must equal 1, and I have that a plus 4c must also equal 1. And if I want to solve these two, you could just subtract one from the other. So if I subtract this guy, a minus a cancels. C minus 4c is a -3c equals 1 minus 1 is 0. So c must equal 0. And if c is 0, well, then that means that a must equal a plus 0 equals 1. So a must equal 1. We'll do the same thing with these two guys. So b plus d must equal -1. And b plus 4d must equal 8. If I subtract, now b's will go away. D minus 4d is a -3d. -1 minus 8 is a -9. So d must equal +3. And if d is 3, then b must equal -4. Okay, so plugging in. Scoot this up a little bit. Your capital X is equal to as plus b. Well, a was 1, so 1s plus b was -4 over s squared plus 4. And then plus cs, so 0s plus 3, d, over s squared plus 1. Yeah, let's clean that up a little bit. That is s minus 4 over s squared plus 4 plus 3 over s squared plus 1. Okay, we are about there, right? Only problem is, okay, so I've got an s minus 4 up here. I don't have an s minus 4 on this s squared. So instead, I'm going to split this fraction up, right? This is, you can do that as long as you put the first guy over the entire denominator minus the second guy over the entire denominator, right? So I've got, this is, I'll come over here. Big X, capital X is s over s squared plus 4 minus 4 over s squared plus 4 plus 3 over s squared plus 1. Okay, almost there. We're going to manipulate this just a little bit. This guy's not a problem, right? This is cosine of 4 is 2 squared, so this is cosine of 2t. This one, though, with the number up here, it would be sine. But remember, the number up here, your a, this needs to be a squared. So I'm going to rewrite this as, okay, so the s over s squared plus 4 is not a problem. This guy, though, it needs to be a 2 up here if this is a 4. So I'll write 2 times 2 over s squared plus 4. Yeah. And again, here, you got a number up top, a number here. That means it's sine also. But this is a squared, so 1 squared, that means this needs to be a 1, so I'll factor out that 3. 1 over s squared plus 1. Yeah, because then this guy is cosine of 2t, this guy is sine of 2t, and this guy is sine of t. Yeah, because these are the Laplace transforms of these functions. And so that means little x is cosine of 2t minus 2 times sine of 2t plus 3 times sine of t. Lovely. Okay. And, you know, if you go and you plug these back in, they should work. Not that you usually have much time to double check your work on a test, but, you know, if you want to check yourself, you can, right? You just find the first derivative of this guy and the second derivative of it, and then you plug it into the original guy. Keep in mind, you do have to satisfy the original conditions, right? So for this one, x of 0 was 1. So when you plug in a 0 into here, cosine of 0 would be 1, sine of 0 would be 0, sine of 0 would be 0. So x of 0 is 1. Like, make sure that's how it needs to satisfy the equation, but it also needs to satisfy the initial conditions, and that's where the coefficients come in. That's where they're important. Because you may get the right functions, but without the coefficients, it won't satisfy those initial conditions. All right, one more example. We are, oh my gosh, I hope I don't take up more than one page. We're going to solve this using Laplace transforms. Ooh, this looks funky. Okay. All right, let's do Laplace transform on the whole thing. Yeah. Do both sides of the equation. All right, so Laplace transform on both sides of the equation. And when you do Laplace, remember it's a linear transformation, so we can distribute this into each of them. Laplace transform on little x is capital X. Laplace transform on 1 is a 1 over s. Laplace transform on t is a 1 over s squared. All right. And then, oof, what is this? Well, hopefully you recognize that this is the convolution. It's actually the convolution of t and x. Yeah. Just as a reminder that, I'll come down here. If you do the convolution of f and g, it is the integral of 0 to t of f of t minus u times g of u du. Yeah? And so if all you see is a t minus u, well, that means that f of t, right, is t. I'll write it up here. F of t is t, and then g of t is x of t. I mean, technically technically it's t, right? But then because we're doing it of u, then x of u. Yeah? Okay. So this is the convolution of that, which, if you remember, if you do the Laplace transform on the convolution of t and x, that is equal to the Laplace transform of t times the Laplace transform of x. Yeah? Nice. Okay, so if I'm doing the Laplace transform on this guy, I want the Laplace transform of t. Well, that's just 1 over s squared times the Laplace transform of x, which is just capital X. Yeah? Our goal is to solve for capital X, so I would subtract this over. So I've got capital X minus 1 over s squared capital X. I guess I should have factored that out, whatever. And then I got 1 over s and a 1 over s squared, so that becomes an s plus 1 over s squared. So just got a common denominator. It's like times s and times s, right? Let's factor out this capital X. I'm left with a 1 minus 1 over s squared. Yeah, okay. Get a common denominator here, and that's an s squared minus 1 over s squared. Solving for capital X. I wrote this in the wrong spot. You're going to divide by this, right? So you'll have an s plus 1 over s squared. Dividing by this means I'm multiplying by its reciprocal. So an s squared over s squared minus 1. It's just a side note over there. Okay. Oh, well, that's nice. Those guys cancel. And s squared minus 1 is, so it says s plus 1 over s squared minus 1 is an s plus 1 times s minus 1. Bye-bye. So capital X is 1 over s minus 1. And if capital X, the Laplace transform of your little x is this guy, well then little x is e to the t. Nice. Okay. That is it for section 5. Not too bad. Go away. All right. I hope you guys have a great day. Bye.